So we are very happy to have Sridip join us online for this seminar on his very recent work, which appeared last month. So Sridip, please.
Thank you for the invitation. So I'll be talking about universality in spin-refined high-energy data in higher dimension conformal field theory. And by higher dimension, I mean D greater than 2. And this is based on this recent paper we put out with Nathan, Jeha, David Simmons, Daffin, and Ishin. All of them who are in Caltech. And there are also our like developments from last year, which in this paper. So I will also review some of the results from the paper I mentioned here, and then based on that we will figure out what we mean by spin refined high energy data of higher dimensional CFT. So to begin, let me remind you that like what we mean by universality. And the famous example of universality in CFT is in two-dimensional CFT, 2D CFT, where we have modular invariance. And using modular invariance, one can show that the density of states at high energy, so delta is a proxy for the high energy, delta is the proxy for the energy, and in the delta going to infinite limit, the density of states rho delta is controlled by a single parameter, and the functional form is of this form, C delta over 3. And here we can see, given any CFT, the density of states is controlled by a single parameter, which is this central charge. So if someone tells you the central charge of the CFT, irrespective of what kind of CFT you are looking at, the density of states is completely fixed. And this comes about because of modular invariance in two-dimensional CFT. So in this talk, the goal is to figure out or characterize or identify the parameters that controls the high energy data in higher dimensional CFT. And whenever we want to characterize or identify such parameters, we should think of EFT, some kind of effective field theory. So the idea is to write down some effective field theory which controls the high temperature behavior. And this effective field theory will be a proxy for modular invariance in higher dimension. So in higher dimension, technically we do not have modular invariance, but using this new EFT, we will be characterizing the parameters and write down a systematic expansion, which will tell us about the high temperature behavior. And using this idea of EFT, we will also answer the question whether there is any universality in higher DCFT in the sense in which I explained the universality in the case of 2D CFT. So yes.
When you say EFT, do you mean, are you connecting it with some ADS bulk theory?
No, at this point, I am only talking about the boundary. So the CFT doesn't have to be holographic. As long as it's a strongly like some interacting CFT is fine.
Okay.
Yeah. And in the later part of the talk, I will mention about some implication in terms of holographic CFT. But for bulk of the talk, it will be about usual CFTs. And I will say for which kind of CFTs we should be applying this EFT. So here's the plan of the talk. First, I will review the results in 2D CFT to to give you a flavor of what kind of results we can hope for in higher dimension. Then I will go to higher dimensional CFT. And then there will be two parts. In first part, I will review the idea of thermal effective field theory, and I will tell you what the density of states in the spin unrefined case. So I will be talking about density of states without mentioning about spin in this stage. And then I will make it spin refined, and then you will ask questions about how are the spin grows as a function of delta and spin, how the density of states grows as a function of delta and the spin. So I will revisit the 2D story in some different light, either in the light of thermal effective field theory, and that will immediately get generalized to higher dimension. And then we will come back to this main point of the talk, which is the spin refined asymptotics in higher dimensional CFT. And we will also show some new features when we write down this thermal EFT in the context of spin refined data. And then we will see there is an extension to fermionic theories, there is extension to massive theories, and if the time permits, I will also comment about holography and non-perturbative corrections to this effective field theory. So is the picture clear? So the main idea is that in 2D we have modular invariance. The modular invariance gives you some sort of results for high energy data. In higher dimension, we do not have modular invariance, but this idea of writing down an effective field theory can play a role of modular invariance and can help us derive similar kind of results. Okay. So let's proceed. So let's first start with the 2D case. So 2D CFT. As I mentioned, the basic form of the universality in 2D CFT is density of states in delta going to infinity limit is universal. And the way we derive it is using the modular transformation and using the canonical ensemble. So we look at torus partition function, torus partition function, z of beta. So basically you are putting the CFT on a temperature 1 over beta. And the modular invariance immediately tells you that z of beta is same as z of 4 pi square over beta. So this comes from S modular transformation. And then the idea is to take, then the point is that this density of states here is controlled by the high temperature limit. So I should be taking beta going to 0 limit of this expression. And here, if I take beta going to 0, the 4 pi square over beta goes to infinity. So here on this side, everything is controlled by the vacuum. So I can immediately write down exponential 4 pi square over beta C over 12, where the C over 12 is related to the ground state energy minus of ground state energy. So in the canonical ensemble, so another way of phrasing this universal result is to say that in the high temperature limit, the partition function z of beta in the beta going to 0 limit is universal and controlled by a single parameter, which is the central charge. And now you may ask that, like, this is just the S modular transformation, but we know the modular group is a big group, is the modular group is PSL2Z. So modular group is PSL2Z, and S modular transformation is only one of the group elements of infinite number of group elements inside this group. So you may ask what happens if we use the other modular transformation? Can we get some refined informations? And indeed, the answer is true. We can get refined information. We can get other gamma inside PSL2Z. As a prototypical example, let us ask what is trace e power minus beta h minus 1 to the power g. So here, sorry. So here you can see, because of insertion of minus 1 to the power j here, it basically weights the even spin and the odd spin with a different sign. So even spins comes with plus sign and the odd spin comes with minus sign. So in some sense, in the microcanonical ensemble, this gives you some information about rho even, rho even delta minus rho odd delta in the delta going to infinity limit. But in the most of the talk, I will not be stating the result in terms of the microcanonical ensemble. So we will only mentioning, or we will be mentioning the result in the form of the canonical ensemble. So the main
Can I
question,
ask a question?
yes.
Yeah. So normally trace e to the power minus beta h, the partition function gives us the vacuum to vacuum transition amplitude, right?
Yes.
So physically weighing with -1 to the power j, what it
Mhm.
should physically mean in terms of like vacuum transitions and things like
So
that.
when you are saying that trace e power minus beta h gives you the vacuum to vacuum amplitude, that happens in the beta going to infinity limit. So you should really think of trace e power. So let me write it down. So if I write it trace e power minus beta h, that's really is this sum e power minus beta delta, where delta. So basically in terms of the, like if I want to write it down in terms of the amplitude, then it's really delta e power minus beta h delta. It's not only sum. Like here the propagation is happening for, like there is a sum over all the deltas. Only in the beta going to infinity limit, this sum projects onto the vacuum, and then you have vacuum to vacuum transition.
Yes.
But here I am taking a different limit. Here I am taking beta going to 0 limit. So in the beta going to 0 limit, this sum is dominated by the states in the delta going to infinity limit. So it's a transition that's happening at a very high energy.
Okay, I see.
So it's not a vacuum to vacuum.
Okay, I see. Got you. Thank
Yeah,
you.
and then when you insert -1 to the power j, so then basically you are considering in the microcanonical ensemble. So okay, let me back up a bit, then I can explain it a little bit better. So a proper way to think about this trace e power minus beta h in the microcanonical ensemble, we generally say that in the beta going to 0 limit, I have this expression here. And if I do an inverse Laplace, I get rho of delta. And why do I get this? Because let me write it down here. Z of beta can also be thought of this way: 0 to infinity, rho delta prime, e power minus beta delta prime, d delta prime. And now from this expression here, you can see that in the beta going to 0 limit, most of the contributions comes from delta going to infinity limit. So the idea is that rho of delta prime is inverse Laplace of z of beta going to 0 limit. And a proper way to phrase this result is to think of some microcanonical window at some high energy and average over that microcanonical window. So basically you write it down this way: d delta prime, delta minus delta, delta plus delta. And so you basically bin the high energy states and you count the number of states inside this window. And that expression is given by the inverse Laplace of this quantity here. But now when you insert this -1 to the power j, instead of summing over this rho delta prime, you basically bin in a different way. Whenever there is an even spin, you count with plus. Whenever there is an odd spin, you count with minus. So instead of doing this, you basically bin this way: rho delta prime. Sorry, I should write a spin also. So there is a spin variable -1 to the power j d delta prime. So is that clear now?
Yes, this is good.
Okay.
Thank you.
Yeah. And one more like technical comment, that normally when I have trace e power minus beta h, and in the microcanonical I have this kind of quantity is all positive definite. So mathematically you can write down some rigorous theorems which basically takes you from the canonical to the microcanonical for trace e power minus beta h. But when you have insertion of -1 to the power j, in the microcanonical you can have oscillation because there is an insertion of -1 to the power j, and the result in the microcanonical ensemble is less rigorous compared to the other version. And this is why in the most of the talk I will be only focusing on this kind of quantity. So in the canonical ensemble the results are more rigorous. When you go from canonical to microcanonical, like not all the things, there might be subtleties.
But in 2D, this is settled.
No, even in 2D, there can be subtleties. Yes.
Right.
Yeah. Yeah, but these subtleties should not matter for irrational chaotic CFTs, where the spectrums are very, very dense. But at the end of the day, what I'm trying to say, in the case of Cardy formula, you can write down some rigorous theorems. But in this case, when you have insertion of -1 to the power j, like you have to be satisfied with physicsy arguments. Like you cannot write down any rigorous theorems at this stage. Okay. So anyway, so the upshot is that like all this discussion is that we will be looking at canonical ensemble. Looking at canonical ensemble, and sorry, and the idea is to look at beta going to 0 limit or high temperature limit of this kind of quantity, trace e power minus beta h -1 to the power j, or more generally trace e power minus beta h e power twice pi I p over qj, where the GCD of p of q is 1. So this is like some rational number written down in terms of two co-prime numbers. And again, when p over q is half, basically we get -1 to the power j. So now how do we determine the beta going to 0 behavior of this kind of quantities in 2D? So in 2D, the way we do this, we basically, so let me focus on, for simplicity, let me focus on this, sorry. Let me focus on this case where we have -1 to the power j. And the idea is that we will be using the following modular transformation, which is 2, -1, -1, and 0. So now this is not S modular transformation, rather this is STS. And if you use this modular transformation on this quantity, then after the modular transformation, the effective beta, so the modular transformation acts like the Mobius transformation, and after modular transformation, the effective temperature, effective beta prime, will be 4 pi square over beta times 1/4. And this just comes about if you use this. So in general, what happens? In general, we write down the 2D CFT partition function as e power twice pi I tau L0 minus C over 24 e power tau bar L0 bar minus C over 24. So if I want to compute e power minus beta h minus 1 to the power j, then you can see that tau is basically what? I beta over twice pi plus half, and tau bar is minus I beta over twice pi plus half. And then this gamma acting on tau gives you A tau plus B over C tau plus D, where these are A, B, C, D. And once you do this transformation, then you will get tau prime to be half plus I 4 pi square over beta or 1/4. So you can do this manipulation. And once you do this manipulation, you have this thing. And now you can see in the beta going to 0 limit, this quantity goes to infinity. So again, everything gets projected onto the vacuum state. So let me write it down explicitly. So this trace is same as trace e power twice pi I tau prime L0 minus C over 24 e power minus twice pi I tau bar prime L0 bar minus C over 24. But now you see that, and the beta going to 0 limit, this quantity goes to infinity. So everything gets projected to vacuum state. So L0 bar is 0. So at the end of the day, I can write it down as exponential 1/4 4 pi square over beta c over 12. So now let us observe the following thing, that earlier we had trace e power minus beta h in the beta going to 0 limit exponential 4 pi square over beta c over 12. And now if I do this minus 1 to the power j in the beta going to 0 limit, I will have exponential 1/4 4 pi square over beta c over 12. In fact, you can do this procedure for any p over q using some other modular transformation, qj in the beta going to 0 limit, and you will get something like this: 1 over q square 4 pi square over beta c over 12. So
Just
that
a question, are there any constraint on the classes of modular transformations allowed, or any modular transformation will do?
So for a bosonic theory, you can do any p gamma which belongs to PSL2Z.
Okay.
Assuming there is no anomaly, CL equals CR, which I assumed CL like C left equals C right.
Hmm.
And for fermionic theories, you need to be a bit more careful, because in the fermionic theories, the P, so for the bosonic theories, spin are integers, so the partition function is invariant under T transformation. But for fermionic theories, the spin can be half integer. So, for example, it might not be invariant under T. So there will be a subclass of modular transformation that is allowed. So the story is slightly more complicated in the fermionic case.
Okay.
Another way of saying this thing is the same way that when you do a modular transformation, the spin structure might change. And so you can go from one spin structure to another spin structure, and you have to keep track of that.
Okay.
But for the bosonic case, this is all general, and this should be valid for all CFTs where C left equals C right. In fact, you can make it slightly general. You can say C left minus C right is 0 mod 24.
Okay. Okay, thank you.
Sorry. Okay, so here, so the one of the main point of main point of telling you this is the following, that here you see that if someone tells you the answer for the partition function trace e power minus beta h, that someone tells you how it behaves in the high temperature limit, from that you immediately can read out this central charge, this coefficient. And once you know the central charge, you can immediately predict these two quantities. So you do not need to know anything else. So knowing this first line basically helps you to derive the second line and also derive the third line. You do not need any extra data to derive the second line and the third line. So in that sense, there is a huge universality. You only need to know the partition function without any insertion, and then you can insert any kind of like rotation fugacity with rational angle P over Q. You know them, and they are indeed controlled by the same central charge. And then there is a factor 1/4 or 1 over Q squared that is completely controlled by this number here, P over Q. So there is a huge sense of universality in the two-dimensional CFT, and that comes about because of you can use the modular transformation. So the upshot is that the modular transformation, or rather modular invariance gives you a huge sense of universality. You only need to know trace e power beta h, and that automatically tells you about all of these grand canonical ensemble quantities for all P over Q belonging to rational. Now at this stage, it's more or less should be clear that this is the same question we are going to ask in higher dimension. So the question we are going to ask in higher dimension is following, like whether there is similar universality. There is similar universality in higher dimensional CFT. Note, in higher D, we do not have modular invariance. Higher D CFT does not have modular invariance. But of course, since I'm giving the talk, of course, the prediction is we can make some statement. We can show that there is indeed some universality, and there we will use the idea of thermal effective field theory to make some prediction. So yes.
Yeah. So does it mean that is the reason why this is happening, that if I look at rho odd minus rho even,
Mm-hmm.
that is not exponentially different from the total rho? Or
No, they are wait.
mean, why is
They are
this happening?
exponentially suppressed because these are down by 1/4.
Yeah, okay, but still there means that there is no J dependence in the right hand
Oh, J dependence meaning here?
in the right hand side of the other two formula.
Oh, no, there is no J dependence because basically, so on the left hand side, it is on counting row even minus row odd. So you are summing over all the spins in some
I mean,
sense.
yeah, right.
So in 2D, you can think of that in the holomorphic case, for example, you can write down Radhamakar expansion. So in
Yep.
some sense, the first term is Radhamakar expansion is controlled by this piece. The second term is controlled by this piece and so on.
Mhm.
So these are some subleading saddles.
Okay. Okay.
And the point, so if you just think of density of states, these are some subleading information in terms of density of states. But then when you add and subtract between different spin, this subleading piece becomes a leading piece for this quantity.
Fine. Yeah.
And then the question is whether these other informations are also universal or not.
Right.
To begin with, it might not be universal because they are subleading informations. But the point is the modular invariance tells you that those informations are also universal and controlled by the same parameter.
Okay. Thanks.
So in higher D, let me be slightly more concrete. So in higher D, what will happen? So I will come back. I will come back and explain this in more detail, but just give you the flavor of what kind of results we are hoping for is the following. So in higher D, the hope is to first write some expansion for trace e power minus beta h in the beta going to 0 limit. And in the beta going to 0 limit, it will look like it will be of the form something like this: a1 d plus 1, a2 minus d plus 3, and so on. And then the question is, someone tells you this thing, this quantity, where you know these coefficients a1, a2, and so on. And if you know these quantities, can we predict the behavior of e power beta h twice pi I p over qj? So can we predict this? If I know these coefficients a1, a2, and a3, and so on. And in higher D, the story is also becomes slightly more complicated because you can have more angular momentum direction, the Cartan directions. So this should really be some like dot product because you can turn on various Cartan directions. Okay. So is the question clear? Good. Okay, moving on. So let me review the thermal effective field theory a bit. So first I will explain how this expansion comes about, and then I will explain how we can derive this quantity knowing this first line. So now I will explain the idea of thermal effective field theory. So to explain the thermal effective field theory, first we need to realize that this trace e power minus beta h is nothing but a path integral evaluated on this manifold. Okay, let me write it down the following. It would be easier. Z is that clear? So basically, this S1 as a cycle length beta, and basically we are doing a path integral over S1 beta times SD minus 1. And in the beta going to 0 limit, basically means I am shrinking the circle of this S1 beta. And when I am shrinking the circle, effectively the theory lives on SD minus 1. So the rough idea is that we should be able to write down some effective field theory, which would be some local functions or local functionals living on SD minus 1. So I should be able to write down some action which only depends on fields that lives on SD minus 1. And this will give us a natural framework to do a high temperature expansion. To make this idea more concrete, what we do instead of SD minus 1, we consider S1 beta times some arbitrary manifold MD minus 1. And let us also assume that on this manifold, because there is a S1 beta, you can write down the metric in a Kaluza-Klein form. So the metric would look like this: d tau minus A square twice phi plus Gij dxi dxj, where this is a metric on MD minus 1, and this d tau minus A is the time direction. This gauge field just comes about because it could be the case that when you have the circle on MD minus 1, this circle can be slightly twisted as you go along the beta direction. So as you go along the time direction, your manifold MD minus 1 can be slightly rotated. And that is basically captured by this gauge field A. And this gauge field A is also a function of the fields living on MD minus 1. So the idea of effective field theory is that in the beta going to 0 limit, if you have an interacting CFT, there would not be any zero mode in this Kaluza-Klein reduction. And if there is no zero mode in the Kaluza-Klein reduction, you can effectively write Z of this thing in the beta going to 0 limit. You can write them as some gap theory, Z gapped, living on MD minus 1, which basically same as saying that it will be Z gapped, and this will only be a function of AI, Gij, and this dilatonic field e power 2 phi. So this is this is a simple argument, but this argument is very powerful. It basically tells you that given any CFT, under the Kaluza-Klein reduction, if the CFT doesn't have any zero mode, which is mostly be the case because for the interactions you would not expect there would be some zero mode, and if such is the case, then under this reduction you should be able to write down some partition function which only depends on AI, Gij, and e power 2 phi. These are the background fields that lives on this manifold MD minus 1.
So also means this is means you also need the space direction to be compact, right? Otherwise, this assumption may not be true.
Well, yes, I need the space direction to be compact. That's true, But you can also think of some limiting procedure where the space direction becomes very large.
Yeah.
So
But
in the
no,
other,
I mean, boundaries are there or not? Are there non-trivial boundaries of MD minus one?
at this point, I am not writing down any boundaries. MD minus one is compact
Yeah.
without any boundary. But indeed, you can think of scenarios where MD minus one have boundary, and then the effective field theory will have some extra terms which comes from from these boundaries.
Which may be gapless.
Yes, which can also be gapless. And the idea is that, so here I am saying that I am assuming this is gapped, but if there is gapless modes, it's not like everything falls apart. You just have to keep track of the gapless modes separately and add their contribution to the part.
But that will spoil the universality, or
No, that will spoil. No, that will only give you a correction of the form log beta or constant, and which are anyway very subleading informations.
okay.
So most of the universality is there. You still have the control, but if there are gapless mode, you cannot predict the coefficient in front of log beta term or the constant piece.
Some
And
universal information will become dependent on that.
yeah, some universality will become depend on this case. Yes, right. But there are various ways to kill the zero mode actually. For example, in our paper, we checked with various free field theories, our prediction, like coming from the effective field theory. But you may think that free field theory will have a zero mode when under the KK
I was
reduction.
thinking about the SPT phases, the symmetry protected topological.
Ah, I see. Yeah, in those cases, you have to be a bit more careful because there are like TQFT living on the slice, and this TQFT will have some extra contribution.
Yeah.
In fact, these kind of cases can also appear if there is spontaneous symmetry breaking.
Hmm.
And then also you will have some extra contribution coming from those things. But those are like some special cases where you can do case by cases. But if you just generally randomly pick any, for example, 3D Ising model, then of course this kind of analysis will hold. Okay. Then let me go through, so now at this point I haven't really used the fact that this is a CFT. Like this should hold for anything basically. And well, I should be a bit more careful. So I use the CFT in the sense that if it's a massive field theory, then I have to be a bit more careful about how I take the thermodynamic limit. So in the CFT, taking beta going to zero limit and taking the spatial size of the manifold to infinity are equivalent. But for a massive theory, those things are not necessarily equivalent. So one should be slightly more careful, but I will come back to that later. So for now, let's think of this as a result happening in the CFT world. So now we also know that the CFTs are like there is a while invariance classically, and there is a while anomaly. So using this while invariance and while transformation, I can also write it down as Z gapped AI Z hat IJ 0, or in this language e power 0, where Z hat is e power minus twice phi G plus some e to the power S anomaly. Now the idea is to choose a scheme, and in that scheme, you can figure out the anomaly term, and you also have to compute the ground state energy or the Casimir energy in that same scheme. And so you have to keep track of those terms by your choice of scheme. And then in the next phase, our main focus will be on this piece here. Like this is the main thing which we'll write down as e power minus S thermal, which only depends on this background field AI and this field G hat IJ. So this will be our thermal effective action.
And the dependence on the scheme, you will not cancel.
So the idea is that dependence on the scheme. So this S thermal doesn't depend on the scheme. So this is a crucial point. So let me write it down clearly. So trace, so I was writing trace e power minus beta h, but this trace e power minus beta h is same as trace e power minus beta dilatation operator plus epsilon 0. Now this thing is same as e power minus s thermal plus e power, sorry, wait a second, minus s anomaly.
Yes.
Now, the point is the S thermal is scheme independent. The scheme dependence only comes in the S anomaly and this epsilon 0. And so you have to keep track of that thing. So you have to choose a scheme and you have to figure out what is the value of epsilon 0 and what is the value of S anomaly in both sides. But on the other hand, you see that like in the beta going to 0 limit, this is a very subleading information again.
Yeah.
Because in the, for example, if you just look at the leading piece, this epsilon 0 doesn't really matter.
Hmm.
But again, the point is if you write down the expansion, then you have to choose a appropriate scheme, and you have to figure out the S anomaly in that scheme, epsilon 0 in that scheme. But this equation is scheme independent. That's the main point. Is that clear?
Yes.
Okay, good. Okay, so now I will focus on this S thermal. So basically, I now write down all the possible terms that is allowed by this g hat ij and ai. So the first term I can possibly write down is, of course, of this form, square root g hat, okay, beta to the power d minus 1. Sorry, wait a second. So the first term is this f, then the second term is c1 r hat, then the third term is c2 f square, and so on, where f square is derived from ai and r hat is the Ricci scalar derived from this g hat ij. Now the main point is that now this is a very general expression, and the point is that this f c1 c2, these are CFT data. So you, for a given CFT, you only need to know this data, what is f c1 c2. Once you know this, you can put this on any manifold md minus 1 and your answer will be given by this same expression. And that's the strength of the EFT, that it basically tells you that once you know these numbers AFC1, C2, which are the intrinsic CFT data, you can put the CFT on any manifold which admits a Kaluza-Klein reduction, and you can write down effective action. So in particular, you can evaluate this on when MD minus 1 is SD minus 1, and then you can write down, then you can evaluate this, and then you will get some expression is thermal is it will be of the form volume of SD minus 1. So minus S thermal would be volume of SD minus 1. I should write it as a minus. If 1 plus omega I square, where this omega I is basically coming from the twist. So okay, I guess I should. So in here I wrote down for e power minus beta h, but instead of doing this, I could have also done the following: h minus I omega j. And if I do this I omega j, then I will find there will be an extra factor of 1 plus omega I square by doing the same kind of analysis. And then there will be other pieces which depends on this r, f square, and so on. F beta to the power d minus 1. And indeed, you can see that in 2D, F is related to central charge. And in fact, you can see F is basically twice pi C over 12. Because if I plug this back in here, then I will get minus S thermal, like e power exponential minus S thermal is exponential 4 pi square over beta C over 12.
So Sridip, is it easy to see why you get the 1 by 1 plus omega square?
Yes, it comes from the fact that if you write down this in this metric in the Kaluza-Klein form, there will be this e power 2 phi, which actually depends on the omega. And then you define this g hat. So there is a 1 or 1 plus omega square dependence.
Oh, I see.
So it just comes from this this thing.
Okay.
And so that's the mathematical reasoning, and the physically is kind of intuitive because so think of this sphere is rotating, and this omega equals I is basically related to the fact that the great circle of SD minus 1 is rotating with the speed of the light. So in some sense, the thermal effective field theory should break down at omega equals I,
Yes.
which is, so if I say, for example, okay, let me write it down. For example, I am computing this quantity, beta omega j. And now see, at omega equals I, this is like beta h minus omega j in some sense. Now, if you look at the operators which are near the unitarity bound, where h is approximately j,
Right.
and then there will be a divergence, is omega is greater than 1.
Okay.
For
Thanks.
example, in the ADS, this is kind of related to this superradiance instability. Like this picture that Siraj and other people had on about this gray galaxy and so on. So yeah, so from what I wanted to say, from the physical point of view, you also expect this piece 1 plus omega square, because the effective field theory should break down at this point.
And Sridip, are there any constraints from any bootstrap-like constraints on these numbers?
No, not right now, but one can possibly hope to write down some dispersion relation and do something. But yeah, I guess we have discussed this a little bit, like in our group meetings, but nothing concrete as of yet. But one can hope. So one can think of a scenario where, so in the dispersion relation, what you do, you basically have like in the dispersion relation, you have like some EFT-like expansion around the origin in some momentum domain, and then you use the fact that in the high momentum would be some unitarity, then you close the contour and do something. Here you can hope to do something like that. In the beta going to zero limit, you have some EFT, and in the other finite beta, you will have some other constraint coming from the unitarity, and maybe one can write down some EFT-like thing and constrain these EFT datas.
Because Shagulia had some recent paper on constraining.
Yes, but well, I don't know how much of, okay, maybe it's
I've
so I
not
should
read.
not say anything.
Yeah. Anyway, yeah, let's move on.
Yeah, I can make my comment later about this. Okay, so you have this, okay, so the main point is you have this expression here, and there is a leading term, and then you can evaluate this r hat, f square, and everything. And now the question is, once you know these coefficients, and coming back to the main point, that whether one can figure out trace e power minus beta h minus 1 to the power j, or in general e power twice pi I p over qj. Now you must, in the first glance, you might say that we have already evaluated this quantity, which is trace e power minus beta h e power I beta omega j. So why can't I just replace this beta omega with this finite number e power twice pi p over qj? But that we cannot do because precisely of this pole that is present in this expression. So if I want to take this answer and replace with this, then I have to take a limit where beta omega goes to a finite number. And because I am taking beta going to 0, this means omega goes to infinity. And definitely this is way beyond the validity of this effective field theory, because there is a 1 plus omega square. So that means I cannot use this effective field theory that I wrote down here to derive expression for these quantities. And this is also clear in 2D, because in 2D, for example, where did I write down? So in 2D, if you, instead of computing this, you could have computed the following quantity: trace e power minus beta h, e power I beta omega j. Then the answer would have been exponential 4 pi square over beta, 1 plus omega square, c over 12. And clearly, if I substitute beta omega with this twice pi ip over q, I would not land up with this answer. So in 2D, we can see it directly, and in higher D, we can see it by saying that the effective field theory breaks down. So we need to be a bit more clever, and we need to write down a different effective field theory, or somehow write down an effective field theory and evaluate it on a different background. So in the next step, I will rederive the 2D result using some different argument, and the hope and the idea is to like promote this argument to the higher dimension, and then we will have results in higher dimension as well. So let us go back to the 2D case. Let's go back to the 2D case. So what is trace e power minus beta h minus 1 to the power j? So this is the following thing. Let me draw. So you have a torus where the time length is beta and this one is L, and let's say divide it into two pieces where you have L over 2 and L over 2. And insertion of minus 1 to the power j means that as you go in the time direction by beta, you also rotate by pi. And that means you are basically doing a path integral where you have some modified identification like this. So this thing gets rotated by pi. So this thing gets rotated by pi and comes here. And these things goes here. So I will have this, this identified with this, and of course these two things are identified. So this is the path integral representation of trace e power minus beta h minus 1 to the power j. Now the idea is that now we have two pieces where these two rate things are identified. Now because there is a notion of locality in the path integral, I can just cut off these two pieces and I can take this piece and stack it on top of each other, because this thing is identified with this thing, so this procedure is allowed. So if we do this gymnastic with the pictures, we will get something like this. So now I have beta here, L over 2 here. These things are the red things are identified. Now this green line, dotted line becomes this green line here. So this is the green line basically. And this is also the green line. So this thing is identified with this. And this part is identified with this part. And this line is identified with this line. Now I can take, now this is in the nice form. Now I can take in the beta, now I can take the beta going to 0 limit in this direction. Now if I take a beta going to 0 limit in this direction, what I effectively have done, so I need to write down an effective field theory where my effective beta is twice beta, because this cycle gets twice, and the effective size of the spatial circle, so effective L becomes L over 2. So I need to evaluate our original thermal effective field theory, but on a different background with different parameters. So our original effective field theory was what? It was exponential 4 pi square over beta C over 12. But now I basically do this replacement. So I take this thing here, and instead of beta, I do twice beta, and the L over, there is L and it becomes L over 2. So there is another factor of half. And that precisely gives me the answer I want, which is exponential 1/4 4 pi square over beta C over 12. Now, instead of -1 to the power j, if we have e power twice pi I p over qj, then basically I have to piece this torus into q pieces and then stack them together. And if I do this stacking, then again, the beta goes to q beta and L goes to L over q, and this gives me a factor of 1 over q squared. So is this argument clear? Okay, good. And so, and then the idea is that this argument doesn't really rely on the modular invariance, and whatever I said is nothing specific to 2D. So this argument can easily be generalized in higher dimension. So the rule of the game would be following, that log of trace e power minus beta h e power twice pi I p over qj in the beta going to 0 limit will behave like -1 over q trace e power minus q beta h plus some other terms which I will come back later. So this is the main leading piece of information. So sorry, there is a log here. So this beta goes to q beta really just comes from stacking things on top of each other. And this 1 over q factor comes from the fact that your spatial manifold gets divided into q pieces.
Sorry, Sridip.
Yes.
Some of those arguments about matching in the picture above relied on modular invariance, no?
Wait,
none of
which of
that.
those
So
matching?
for example, the mapping, I didn't, for example, the mapping the left and right, the beta, the triple arrows, didn't they?
Oh, this one? No, this is just a torus, right?
So I see.
I mean, this is just a torus. So the point is that in the higher dimension, instead of you will have SD minus 1, and then you will have S1. And then the idea is you piece the SD minus 1 into 2 pieces. And then as you go along, these 2 pieces as you go along the time direction, these 2 pieces get exchanged. So the
Okay.
point is that the identification, so the main point is that this thing and these things are identified, and this thing and these things are identified. And this triple arrows doesn't really, is just go along the right if you're worried
Mhm.
about.
I see. So it doesn't require modular invariance, but it requires like a circle. Is that
Which one requires the circle?
I didn't so in higher dimension it still follows because you have a SD minus 1.
Yes, in higher dimension it follows because you have S1 and times SD minus 1. So this S1 is still there. So this line is also identified with this line. So instead of this being an interval, just think of them as a part of the sphere.
Okay. Thanks.
If
And-
it was, if there were different boundary conditions in the space, then this would not work, right? In the left and the right side.
Well, it's the SD minus 1, there is no
No,
boundary.
no, I'm saying if it was not SD minus 1, if it was
Oh, if
open,
it is some other manifold, yeah, then you have to be, yes. If it has some other features, then you have to be careful about how they talk with each other. Yes, right. But as long as it doesn't have any boundaries, as compact, then
Yeah.
this argument holds.
Hmm.
And more precisely, what we are doing is the following thing. Like, let me write it down like in a more precise mathematical way. So the claim is that trace e power minus beta h e power twice pi I p over qj is same as computing the partition function on this manifold S1 q beta times SD minus 1 modded out by ZQ, where the ZQ action is following. The ZQ act on unit vector n on the SD minus 1 and tau as following way. It basically rotates the unit vector by n hat, by r times n hat, and advance the tau by tau plus beta. And what we are doing, we are taking this S1 q beta times SD minus 1 and we are quotienting by this ZQ action. And in the beta going to 0 limit, this manifold can be approximated by SD minus 1 slash ZQ times S1 q beta, approximated. And then this is the one replacement rule where beta goes to q beta, and this gives you the 1 over q factor in the volume. And that explains the rule, the 1 over q here and q beta here. So is that clear?
Sorry, what is R there? Missed it.
Oh, sorry. So okay, so r is the rotation. This
Okay.
so r to the power q is 1.
Okay, thank you.
Yeah. So yeah, so basically this is ZQ element here. So, and also like here I should make one more comment that the fact that we have SD minus 1 didn't really play much of a role here. As long as we have any compact manifold MD minus 1 and it has some isometric group, I can insert this isometric group, like isometric group of finite order. I can insert this isometric group in the partition function and I can play the same game, because it's exactly doing the same thing. So instead of doing this thing, I would be doing here, I would be writing MD minus 1 and I would be quotienting by the same ZQ. Okay. Now this argument immediately goes through in higher D, and in higher D we immediately get this result, which is trace e power minus beta h e power twice pi I p over qj e power I beta omega j is volume SD minus 1 if q to the power d beta to the power d minus 1. So in 2D we had q square. Here I wrote down somewhere, I guess. Here 1 over q square. This becomes 1 over q to the power d in the leading order. And not only that, I can also evaluate the other terms, and I just have to do this replacement. Like there would be a 1 over q coming from the volume factor, and whatever the powers of beta, I have to change beta to q beta. So the next term would be 1 over q beta to the power d minus 3, for example, and so on. So one part of the data is completely fixed by this analysis. But in higher D, this is not all the story. There are more to it. And now I will explain some of the subtleties. So the first subtlety is the following, that which I immediately said here, that here I have said that this manifold is here S1 q beta times SD minus 1 slash ZQ. These are approximated by this quotienting thing. But of course, this is a non-trivial bundle over like SD minus non-trivial bundle over this SD minus 1, because as you go by, so because there is a simultaneous action of this ZQ, because when you act ZQ on this n hat and tau, tau advances by beta and n hat advances by this rotation. So, but on the other hand, on this manifold, there is no such identification. So these two manifolds are globally different. So that means your effective field theory can have some topological term which are sensitive to this global structure. So, and in general, so that means here I can have extra pieces, which is S topological. And one example of this kind of topological term is you can consider a 2D CFT where CL is not same as C right, but it's still 0 mod 24. And then the answer would be slightly different. In 2D case, you will see that there will be exponential 4 pi square over beta, C over 12, and times there will be some term which depends on mod Q and some pieces here, which depends on CL minus CR over 24. And then there is a twice pi I. So here you see, and this P inverse mod Q is, you are just doing the inverse in mod Q sector. So the point is, because CL is not same as CR, there is a gravitational anomaly. And when you do this reduction, and this gravitation, because of this gravitational anomaly, you can be sensitive to this extra global structure of this manifold. And because of this extra structure of this manifold, there can be this extra piece. So in principle, like in higher dimension also, like there can be gravitational anomaly, and you can possibly write down this topological term. We haven't attempted to like write down or classify all possible terms in higher dimension, but in principle one can do it. Okay, so that's one subtlety about topological terms. And the next subtlety is the following thing. The next subtlety is the fixed points. So what about fixed points? And these are also new features in higher D. New features. By the way, how much time do I have? I completely
Yeah, maybe if you can wrap up in 5-10 minutes.
Okay, I will just mention, yes, okay, sure. So the point is that when we are doing this manipulation in 2D, I know my S1. So for example, say I am doing -1 to the power j, the S1 gets rotated by pi. And when the S1 gets rotated by pi, there is no fixed point of this rotation. But on the other hand, suppose you are doing S2 times S1, then in the beta going to zero limit, there is an issue, because in the beta going to zero limit, there will always be a north pole and the south pole, which are the fixed point of the ZQ action. So the ZQ action has fixed points in beta going to zero limit. And that means those fixed, so those fixed points can lead to new contributions in your effective field theory. So again, going back to this equation here, let me copy it. Here, we will have extra pieces, which we call S defect. And then one should write down some effective field theory, which has support on this north pole and the south pole of S2 times S1. So this is some new EFT data supported on higher codimensional manifolds. And again, these are subleading because these are higher codimensional objects. So the first term that you can write down is basically, for example, in S2 times S1, these are points. So the first term you can write down is some constant piece. The second term you can write down will go like proportional to beta. Then the other term you can write down is proportional to beta square, and so on. So they will always be subleading. But again, the point is that you can play the same game that I played for the whole manifold. Like when I did the S1 times MD minus 1, you can use the same kind of game and you can write down the EFT. There will be some new set of data which will characterize these defects. And again, the point is there is some sense of universality. Once you know a CFT, you just need to determine these coefficients. And once you know the coefficients, you can plug in like you can use those things, you can use those Wilson coefficients for those kind of defects. So you only need to know what kind of defect it is, whether it corresponds to. So this defects is coming from some rotational group element. So you just need to know like which rotational group elements the defect corresponds to. Once you know that information, you know the CFT, you can write down the Wilson coefficients and you write down the EFT data. That like this S defect.
So even in free theory, you will get a contribution.
Yes, even in free field theory, you can get a contribution. Right, exactly.
That has been computed.
Yes. So that's the final thing. There are three final things I want to briefly mention. So one thing is that everything I have just mentioned, we checked against free field theory, like in all possible generality. Because in free field theory, it's easy to compute this trace e power minus beta h because you can write down the plasticity exponential and you insert this minus 1 to the power j, and then it becomes a word counting problem with some particular weights. And then people have developed lots of techniques to figure out this limit. And once then you can do this expansion and figure out what are the Wilson coefficients. And it exactly matches all the universality that we predict. And then we can also do it for holographic CFTs. For the holographic case, all you need to do, you need to so we said that you need to take this boundary and basically expand it in the bulk. So the idea would be to, for example, in ADS3, you take a BTC solution with a Q beta temperature, inverse temperature, and then you just do this quotient and keep the radial direction like untouched. So you keep the radial direction as it is, and then on the other direction, you basically do this quotient. But there is some subtlety on the holographic case. In ADS3, for example, there is fine because this quotient is smooth, there is no fixed point. But in the higher dimension, for example, if you do it on S2 times S1, then the North Pole and South Pole are the fixed points. So when you go to the tip of the cigar in the bulk, that creates a singularity. And there should be some mechanism which resolves the singularity, and that mechanism will also basically will tell us all the Wilson coefficients that appears in the holographic CFTs of the S defect. So the point is, in the holographic CFTs, all these Wilson coefficients are fixed. Like you just compute some black hole entropy or black hole free energy, and that immediately gives you all the coefficients that appears on this side. And if you have fixed points, then there will be a singularity in the tip of the cigar, and somehow that should get resolved. And that mechanism should also give you S defect for the holographic CFTs. So that's one thing to think about, like what would be those actual smooth solutions for the cases where you have this singularity in the bulk. And finally, I should mention about fermionic theories. For the fermionic theories, the story more or less goes similarly. Just you have to keep track of the spin structure. So, for example, if you have normally if you have antiperiodic boundary condition, but suppose you are stacking two pieces together. So that means if the fermion is antiperiodic when it goes from tau to tau plus beta, it becomes periodic when it goes from tau to tau plus 2 beta. And when it becomes periodic, you have to insert a minus 1 to the power f. So depending on whether p plus q is odd or even, you might have to insert minus 1 to the power f when you compare this side with this side. And that you can just write down systematically what happens. So, but the main, for the fermionic theories, the main point is that there are two kind of independent data. So for fermionic theories, we have trace e power minus beta h and trace e power minus beta h minus 1 to the power f. Once you know the Wilson coefficients of these two expressions, then you can figure out everything else. So, and that is kind of the main punchline, that for any CFT, once you, whether it's bosonic or fermionic, once you know the Wilson coefficients that describe these two quantities in the beta going to zero limit, you basically know all the leading behaviors of all the other quantities involving trace e power minus beta h, e power twice pi I p over qj, with or without minus 1 to the power f. And there can be new data coming from the defects in case there is fixed points. And those will be some new set of data. And that can only happen in some of them, like that depends on, like for example, in two-dimensional CFT, the defect will never appear. But in three-dimensional CFT, the defect will always appear because there will be always fixed point and so on. And the final point I want to make that, so this stacking argument where I take this piece and put it on top of each other, that argument doesn't really rely on the fact that it's a CFT. So it also works for massive field theory. And in the massive field theory, the proper thermodynamic limit is the L going to infinity limit, rather beta going to zero limit. So we need to rephrase some of the results I phrased in the L going to infinity limit. But the main point is that this replacement, that beta going to q beta and L going to L over q, still holds. So this equation here, the one I wrote down, this equation is still true for massive theory. And we have explicitly checked it for a massive scalar field theory. Like you take some mass parameter m, and then in the m going to zero limit, it becomes like a free CFT. And in the m going to infinite limits is the massive trivial phase. So, and then you can check that this works non-perturbatively for every value of m. Yeah. So yeah, that's more or less what I wanted to say.
Thanks a lot, Sridip. We can take one or two questions. Already had few.
So is it clear that, say, if you have string theory defined on this orbifolded background, this fibered orbifold, that it makes sense that it will be non-singular? Because most orbifolds are fine, but since it's a fibered orbifold, I just want to know if you have.
Oh, you mean no, I wouldn't say it's not very much clear, but I would hope that so are you thinking of are you asking the question in context of like regularizing this orbifold singularity at the tip of the cigar, or in general from the CFT side?
In general, yeah. I mean, orbifolds of cigar do make sense. I mean, you can if you take a 2D cigar, for instance, and you can do an orbifold, it's a sensible background for string theory. So I was just wondering if these higher dimensions, I guess it's harder to see for higher dimensions.
Yeah, I guess, I don't have anything intelligent to say. Like we were at some point hoping that there should be some mechanism like that. So one thing is, like, for example, so when you have CFT3 and ADS4, so near the tip of the singularity, like it almost looks like C2/Z2. But then we were hoping we can do something, some blow up thingy. But then the issue is that it's not really a flat space, because at some point you have to glue it back to the ADS. So yeah, I don't have anything concrete to say. I mean, but definitely if ADS CFT works, there should be something, right? No, I mean, the CFT prediction is very concrete.
Right.
And then we check it like for like all possible free field theories with, and oh, I see, I forgot to mention one more thing. So you can make it slightly more general. For example, you can insert here some other global symmetry V, and then it becomes V to the power Q here. So you also check these cases, that so you insert some extra symmetry and extra stuff, and then also it works.
So it works, meaning what? That you compute it from the holographic side, or what does it mean?
Oh, so when I say it works, I mean that so for the free field theory case, I can evaluate this side and this side independently by using word counting problem. Because you know the complete field.
Yes.
And that's a complete independent computation, because we are not using path integral or anything. And from the holography side, when I say it works, it kind of almost by definition it works because we are constructing a solution which is like, so we are constructing a solution which follows this quotienting procedure here. And because then you can evaluate the gravitational action, and this quotient almost gives you the answer what the one you want on your nose.
This
Because
fibered one, you mean, not the in a fibered in the sense the ZQ that acts on both the S1 and the SD minus one. That's
yes,
what you
yes,
mean?
the fibered one.
Okay.
Yeah, right,
Okay.
right. Yes, if you do the fibered one, so if you do so suppose you take some solution and do the fibered quotient, then the only problem is there might be singularity at the cigar, but except that point, everything else is smooth, and that if you compute the action, it gives you the right answer. And in ADS3, you don't have to worry about that because in ADS3 it's the smooth solution, so it works perfectly. In fact, in
Okay,
ADS3
thanks.
you can show that it's some SL2Z image of the BTZ black hole, which it should be because.
Right. Okay, thanks a lot, Sri. Yeah.
Yeah, sure.
Just clarifying what you said. So I don't know this, but people add something called the Hayward term at the if there is some angular singularity.
So is this related to this when they have some conical deficit or things like that? There are some extra pieces in gravitational action.
Yeah. So, but what you are saying may not be related to that, or
No, I think it's a more severe. It's I think the issue is we do not like any solution which the curvature becomes infinite and it becomes smooth. So it's like a solution to GR equation with the ADS, like with a negative cosmological constant everywhere except at the singularity. And on the CFT side, we do have CFT side, it tells you that there is a S defect. So there is some extra contributions.
right.
So from the bulk side, you do know that whatever be your smooth solution be, that would resolve the singularity.
Yeah.
And as resolution procedure will also give you this new data.
Yeah.
But then this requires some this requires figuring out what would be the actual solution and that seems like a hard GR problem.
Yeah. Okay. Thanks a lot. So I'll stop the recording.